Hello, my name is Hasib Tariq Khan, and I would like to welcome you all to my presentation on emerging memories. Some of the memories we will be covering would be 3D crosspoint, VNAND, and hybrid memory cubes. I'm a graduate student of electrical and electronic engineering, and this presentation is in partial requirement to EEE 236 Semiconductor Physics course. I'd like to give you a brief outline of what the presentation consists. There would be an introduction to the emerging memories, a basic outline of a technology trend, how they are moving towards faster and denser memories nowadays, a technology timeline consisting of how the technologies have evolved over the period of time, keeping in regards of the size and density. And then we come to the main point of our presentation, the emerging technologies, basically consisting of 3D crosspoint technology, hybrid memory cube, and VNAND. Then at the end, I'll move on to the conclusions. On this slide, I would like to give you an introduction of my presentation. Basically, any computation is based on process and data. And this could be in a signal processing unit, on a microprocessor, on a processor, on a CPU, on larger machines, or any computational element of small or larger scale. Basically, their performance is assured with a fast processor and adequate faster memories. Memory development is nowadays funded by advancements in semiconductor industry. Basically, they are funded by companies like Intel, Micron, and NXP. The key factors we look at when considering the evolution of memory are high performance, lower costs, and high density. A major breakthrough was recently achieved on 3D crosspoint memory. This was This was providing all the three factors like high performance, low cost, and high density. How it provided is shortly mentioned in its name. It uses all of its dimensions. Basically, it's a 3D. So when comparing to a conventional planar 1D memory, it is taking up more density, but increasing the performance by acting in all directions within the spaces provided. As we go on to the details of this presentation, you will figure out more about 3D crosspoint memory. Moving on to the slide on trends. The trends nowadays are on faster and denser memories. As memory, I mentioned, is the integral part of any computing, any processing system. Computing is done on data, and all data is put on storage. So the longer it gets to take, process data, or release an output based on that data, the slower the memory is. Hence, to generate timely outputs based on clock processes, it's recommended to have faster memories. With development of multi-core, parallelism, and overclocking processors, the need for substantial memory grows exponentially. It is expected that by 2020, we would actually be looking at 44 trillion gigabytes of memory, basically consisting of the data we create and copy annually. It would be around 44 trillion gigabytes. Where would such information be stored? Hence, there is an overall need for denser and faster memory. Here I would like you to introduce a concept called memory wall, which is the divergence between the processor and the RAM speed, and it is kept in according with any system, any new memory technology that's being developed. Moving on, On this slide, I would like to show you a memory timeline. Starting from 1947 till 2015, the picture on this slide shows you an overall pattern that's being followed. A basic RAM of 1947, the memory has evolved to a 3D cross-point in 2015. You can look at the last major manufacturing memory, NAND flash memory. As you can see, it was small, sizable, denser, and now it even comes up on sizes till 128 GB. The NAND made a huge market impact due to its size. It was quite fittable even in your pocket, its erasability, and reprogrammability factors. Basically, the size of a basic hard drive nowadays comes on a basic flash disk. 3D XPoint is still a quite recent advancement in non-volatile memory technologies, and it's still in the process of being properly manufactured. From a random access memory in 1947, the process evolved to a programmable read-only memory in 1956, and then it evolved to static random access memory, and then to a dynamic random access memory. Coming down to 1971, we had erasable programmable read-only memory. And nowadays we are looking at technologies like flash memory, which are quite marketed at now. 3D XPoint is still being considered as a major breakthrough, but it isn't been properly marketed. Intel and Micron are still in the process of manufacturing memories in the form of 3D XPoint. Moving on, before jumping onto 3D XPoint technology, I'd like to explain non-volatile memories. Non-volatile memories are a type of memory that can retrieve information even after they have been power cycled. They can be used as long-term persistent storage or even as secondary storage. Mainly, devices like flash memories fall under the categories of non-volatile memories. Moving to 3D XPoint technology. We will start off from its name to make things simpler. 3D in 3D XPoint refers to stacking up of memory units on top of each other. The cross refers to connecting wires looking like a cross from top view. It's basically an array structure with parallel and perpendicular lines. Each cell is identified by intersection of the wires. As you can look at the slide and see that the speed of a 3D XPoint is 1,000 times faster than a basic NAND flash memory. Its endurance is 1,000 times the endurance of a NAND device, and it's increased in density by 10 times that of a DRAM. As you can see, it's mentioned in terms of trade-offs that the speed is high, the cost is low, and there's no volatility. Hence, it falls under non-volatile memories. These trade-offs are considered nowadays hugely to impact the speed, the cost, and volatility to make a smart market decision. As I mentioned earlier, the 3D XPoint technology consists of an array type structure. The perpendicular conductor contains 128 billion densely packed memory cells. As you can see, there is a word line, bit line, and these are the memory elements. Each memory element has a memory cell. Each cell stores single byte of data. They are stacked in multiple layers, and cells are selected by read-write, which are affected by varying voltage. So memory cells are accessed by varying level of voltage to each selector. In contrast to traditional memories, same memory in a 3D XPoint can be used as system memory and storage memory, hence eliminating the need to communicate in between. Memory cells at intersection of word and bit line enable individual addressability. This leads to higher density, as cell switches stay faster than any existing non-volatile memory, As you can see in the picture, the DRAM is high on performance but low on density, and the NAND is high on density but low on performance. The 3D crosspoint performs a perfect trade-off for us here. This slide consists of a basic outline of the stuff that I've mentioned earlier. It has a crosspoint structure, it's stackable, hence 3D. It has a selector line which is selected on varying voltage, and it has perpendicular memory cells. And it is 10 times the greater density than DRAM. It transforms the memory hierarchy because maintaining both of them come together, and high endurance and falls under non-volatile memory. Moving on to hybrid memory cube. Hybrid memory cube is a single package containing 4 or 8 DRAM on one logic die. They are stacked using silicon via TSV technology. Hence, memory is organized. This is a basic hybrid memory cube architecture. The logic base here provides a wide, high-speed local bus for data movement and reduced memory controller complexity, increasing the efficiency. HMC can be used as a near memory, as a level cache, or C-level far-off memory. This is a cross-sectional hybrid memory cube architecture. Internal closed-bank memory architecture is a built-in memory controller for each vault. This enables the availability of post-assembly repair capability, and in-field repair ensures good reliability. It has been divided into multiple DRAMs, 4 to 8. This allows maximum device availability, optimized management of energy and refresh, and better error detection coverage. Moving on to vertical NAND device. Basic SSDs store data in the form of cells. To increase the performance, the cell size has to be reduced to fit more of them in limited spaces. Smaller cells results in less cell-cell interfaces and increased amount of errors. With reduction of cell size reaching the threshold, stacking has become an option. Stacking of cells allows for greater density and increase in performance without increase in size and mutual interference. This is optimized perfectly using vertical NAND. Vertical NAND relies on charge-trap flash. This is an insulating film using silicon nitride where the charge is placed. Traditional NANDs use floating gate approach. When insulated conductor stores the charge. The memory density is 3.5 times better than normal NAND model. As you can see, the graph shows us a 2D planar view evolving into a 3D vertical NAND. It's basically reducing the nanometer length and increasing the stackability, the latest being 128 GB. The latest I heard in the newspaper last week was a 48-layer 256 GHz 3-bit level multi-level cell, which in fact uses 50% less power than the NAND. It has 10 times the endurance and twice the density and the read-write speed. In conclusion, I'd like to introduce you a concept known as Amdahl's law. Amdahl's law is a formula used to find the maximum improvement possible by improving a particular part of a system. In parallel computing, Amdahl's law is mainly used to predict the theoretical maximum speedup for program processing using multiple processors. Basically, it refers to the improvement of a particular part in a system and its subpart and how can it be improved. As I've explained on the slides, that the need for faster, denser, and inexpensive memory is always on the chart. The use of robust memory has its computations in cloud computing, healthcare, aerospace, information, data processing, and data science nowadays. The introduction of blockchain technology has enabled us to work towards faster computing systems nowadays. What will this help? It will help in contributing to a world with increased comfort, stability, and reliability, as has been the general trend. I hope you enjoyed my presentation. Thank you, sir, for giving me this opportunity. Have a good day.